its super heavy booster to launch the whole stack into Earth orbit. That is 120 meters high, or 25 stories. You imagine that, 25 stories. That's halfway up the Sky Tower, to give you an idea in size. So crank up the volume, guys.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have the clock.
Pretty cool, huh? Yeah. And about 8 or 9 minutes later, you're in space. Yeah, a lot of fun. So, I'll put this image in here because when you're in space, and I mentioned earlier on, there's two of the biggest challenges in going into space, particularly long duration space. One is the most obvious, that's that little video clip was all about, weightlessness. And the other one is far more deadly. And you can't see there, it's invisible. You can't see it, can you? What is it? Radiation, yeah, that's why we're here. Right, so Astronaut Radiation Exposure is the title for today's talk. And we're going to be looking at radiation exposure in human spaceflight. We'll incorporate Mars-bound, the International Space Station, what they experience and countermeasures, and the Artemis crews. You know, Artemis II is sitting on the launch pad, ready to go as soon as they get the next wet rehearsal all okay. And I'll answer the question, is radiation going to be a showstopper for going to Mars by 2040? Okay, so I've broken it down into these sort of 6 main chapters, if you will. So I'm going to talk about what is radiation and why does it matter. And I'll talk about where does radiation come from, all this radiation we talk about, and why does it seem to be only a problem in space? Why don't we have to worry about it every day here? I'm going to talk about the radiation effects on the body, acute and chronic, and how much radiation is acceptable, what's okay for the astronauts and what's not okay for the astronauts. We'll then talk about the countermeasures astronauts use for going into space, and then we'll sum up and conclude, and then we'll have questions at the end, just to keep the flow going. So let's look at what is radiation. So everyone talks about radiation, you go and get your X-ray done, and the radiologist, the radiographer scurries away, puts their leather apron on and scurries away. In the room you go, and they hide into another room and so on. What is this thing called radiation? And let's have a look at it. Well, the bottom line is radiation is a form of energy in one of 2 ways. One is it can be in the form of waves, which is light. And I'll come to that. It's a nice little handout, and there's in the handout it talks about light as a wide spectrum to talk about. Or particles, high-speed particles travelling through space or matter. So it can be in the form of particles, or it can be in the form of waves, as in electromagnetic waves, or what we know as light. So that's sort of essentially what radiation is. And then it's split into 2, non-ionising and ionising. The word ionising means to bump an electron off an atom, which we'll talk about. So non-ionising radiation refers to weaker, lower energy. It hasn't got enough energy to disrupt an atom. Just the atom that it strikes remains intact. I put this little diagram up here just to remind you how what we call light or electromagnetic spectrum, and it's got a wide spectrum there from really high energy, short wavelength gamma rays, X-rays, ultraviolet. Then you've got infrared, microwave, and then radio waves here, and visual wavelength that our eyes have adapted to, evolved for, is to look at the visible part of the spectrum. So that's light. So it's these low energy ones here, visible light and your microwave and your infrared and your radio waves, they are low energy. And that's why I remember once when remote controls came out in the late 70s and your TV set, and I remember someone says, "Oh, be careful, you're waving that around." I said, "It's okay, it's infrared. It's weaker energy than normal light, it's okay." So that's non-ionizing radiation. And then you've got ionizing radiation, and that's higher energy light, whether it be in the form of ultraviolet, X-rays or gamma rays, or particles full of energy that are particularly large and particularly at high speed. So they're really energetic, and they've got, by definition, they've got enough energy to bump an electron off an atom. And you might say, "Oh, that's interesting, big deal. What's the point of that?" Let's talk about it. The point is, it interacts with, that ionizing radiation interacts with and damages our tissue, more importantly. And that includes DNA, which of course is important for cell reproduction, which of course leads to mutations and cancers, but also illnesses, infertility and death as well. So it's very important. And I've just put here, this is what ionizing radiation, so you remember probably from high school days, here's your central nucleus that's full of protons and neutrons, that's positively charged, and then you've got various orbits, let's just call them, of electrons and an arrangement around the positively charged neutron. And the idea is that if you've got enough energy from ionizing radiation, you kick an electron out. And an atom minus an electron is called an ion, and hence the name ionization. So that's why it's called that way. So you might say, well, big deal, you've bumped an electron off. What's the fuss about that? The fuss about that is when you start breaking electrons and disturbing atoms, you start breaking or altering critical molecular bonds. And here's a nice little diagram. Here's a nice little molecule. And see, it's been struck there, and an electron's been bumped off, and the bond has been broken. So critical bonds that go to make up molecules get altered or completely broken if one of the atoms connecting involved with the bonding has had an electron bumped off. Because that's what bonds are, sharing of electrons, isn't it? Between various atoms to make up bonds that form molecules. And you start playing around with those outer electrons, booting them off and so on, you're going to upset that bond. And a lot of molecules in our bodies are pretty important to us, pretty essential. So you get essentially cellular damage or death. That's cellular death. So the big one everyone considers is, oh my gosh, DNA. But it also, the process also damages important proteins. Remember our talk on life that we did a few months ago? How proteins are the workhorses of cellular cells in the body. They form structures in the body three-dimensionally. They're involved in all enzymes that facilitate chemical reactions, important metabolic reactions. They are all proteins. So they can disrupt and destroy proteins. The same, we talked about how lipids, we talked about how the cell is the basic unit of life, essentially the atoms of life. And cell membranes with those lipids around them that make up the membranes, they get disturbed as well. So you rupture a cell membrane, that cell's gone, history, dead. So it affects DNA, cellular proteins, and the cellular membranes. And it can do it directly in terms of a strong ionizing energy just comes along and breaks the bonds between the DNA strands here. That diagram is probably familiar to you. It can do a double strand or a single strand break. And of course, the severer the break, the harder it is for the cell to repair. The cells, by the way, can repair themselves. If it's only minor or moderate damage, they can repair themselves. But you do enough damage and the cell can't repair it. So it's directly, or it can do it indirectly. And what we mean by that is an ionization comes along and strikes a molecule within the cell, such as water, H2O. Water makes up 70% of the constitution of cells. 70% of our cells is water, H2O. You split water into hydrogen and hydroxy, OH, and OH becomes what we call a free radical. A free radical is where you've got a molecule and it's unstable. It's had an electron taken off it. So electrons like to be unstable in pairs, 2 and 2, 2 and 2, very simply. They like to be, they're more stable. And you suddenly break up some of those pairs, take an electron off. That molecule is desperate. It'll steal an electron from anything it can get its hands on to make it stable again. And it usually goes to a normal healthy cell or a DNA or a bit of protein or cellular membrane. It'll pinch the electron from there, and that has the same effect. It damages or alters critical bonding within cellular molecules and so on. And that's the point of taking, which we'll talk about later on, antioxidants. You've probably heard of antioxidants, vitamins, vitamin E and C, and as supplements are in your diet. And antioxidants act they quite happily to donate an electron to a free radical, and they remain stable whether they don't care if they give an electron or they don't give an electron. They don't matter. They're stable as they are, but they happily give an electron to that free radical to keep it happy so it doesn't go and attack a cell. So that's how antioxidants work. So you can see ionizing radiation can affect directly or can affect indirectly. Yeah, and the other thing with these ions, because we'll talk a lot about these particles, remember an ion now is essentially a nucleus, either on its own or an atom without a minus 1 or 2 or 3 or more electrons. The larger the ion, so in other words, the larger the chemical element, and the faster it's travelling, the more damage, the more energy it's got, the more damage it's going to do to tissues. That's relevant too, that's going to come up in the talk. So both these processes, as I mentioned, damages the DNA, the molecules, and the proteins and the lipids. So that's what radiation, that's why it matters. You can see now why the radiographer puts your lead apron on and scurries into the room next door and leaves you to it. Away you go, smile. So where does radiation come from? And why is it only a problem in space? Why don't we have to worry about it day to day? Well, there's two sources of radiation, sun and then events within the galaxy, throughout the whole galaxy, what we call galactic cosmic rays, or just events. So let's look at the sun first. And the sun gives rise to two processes that cause radiation. One is just solar wind, and that's just a low flux, relatively low energy particles just constantly flowing from the sun in all directions from the sun, and they come our way. They are relatively low energy particles, and I'll talk about later on, but your spacesuit and the hull of your spacecraft is more than sufficient. The solar wind is not a problem to an astronaut either in the space station or doing a spacewalk or a moonwalk. It doesn't matter. The spacesuit's quite sufficient. But of more concern is the sun has what we call solar activity, where it's got magnetic field lines trying to suppress the hot plasma bubbling away, if you will, on the surface of the sun. And you get build-up of tension with these magnetic field lines, and suddenly they might rupture and burst, and you get what we call solar flares. That's big sudden bursts of X-ray radiation. But also, if it's large enough, big chunks of plasma will come out and get biffed out as well. Plasma is full of charged particles, and known as coronal mass ejections, CMEs. And because they're getting ejected out and there's magnetic field lines involved, those particles get accelerated up to high speeds, because the solar wind is just particles just escaping the gravity of the sun and working their way across to us. But a solar flare is this build-up of energy and magnetic energy, and it just snaps and breaks, and particles get accelerated out at full speed. So they're a lot more powerful than the solar wind. Those events are called solar particle events, or SPEs, and of course related to the flares and the CMEs. So essentially they're intermittent, and they're just sudden bursts of X-rays and gamma rays, the higher ones as well. And you might think, gamma rays, aren't they produced at the core of the sun, and they work their way out over tens and hundreds of thousands of years, work their way out, and they're just visible photons at the end of the day? Yes, but gamma rays also get produced in the high energy events on the surface of the sun. These flares and coronal mass ejections also produce some gamma rays. Do they reach Earth? Yes, they reach Earth. So they are of concern. Now, also that's relevant to this talk is the solar cycles. The sun goes through cycles of being less active and more active. Solar minimum, solar maximum. It's an 11-year cycle. We're currently just in the tail end of a solar maximum. That's why last year you notice suddenly there's all these auroras and stuff with frequency and nice intensity. It's because we've been solar maximum. And it's an 11-year cycle where it'll dip right down low again. So of course that determines the frequency. Solar minimum, you might get one flare once a week. And of course, we only get the experience, the effect from us, if it happens to be as the sun turns around to face us. Sometimes the solar flare might be going in that direction or that direction, but about once a week you get a solar flare, and in solar maximum, you might get, you can get 2 or 3 in a day at times. So they're a lot more frequent and a lot more intense. It's another talk. We do a talk on the sun. We'll do that again this year, perhaps. So that's the sun. The other one is galactic cosmic radiation. What do we mean by that? Out there in the galaxy, there is things like supernova explosions and associated gamma ray bursts, which Nick will talk about next month. And these are high energy events where massive particles just get spat out right across the galaxy to higher velocities, much higher, close to the speed of light, what's called relativistic velocities. And there's a higher proportion of higher mass ions. From the sun, it's mainly protons and electrons with a few alpha particles, that's helium ion, and just a trace of heavier elements up to iron. You get a supernova explosion, as we're going to talk about this year, is how atoms are made, how elements are made. The heavier elements, right up to iron and beyond that, are all produced in supernova explosions. So suddenly you've got a much higher proportion of high mass ions in these cosmic ray, these galactic cosmic rays. So they're going at higher speeds, higher masses, so they're far, far more energetic. So these are the most difficult, the most dangerous and difficult to protect from these high energy particles. So instead of a low continuous, low energy flux just coming from one direction with the sun, with occasional bursts with SPEs, you're getting a low continuous flux, charged particles, but suddenly it's coming from all directions. It's not just coming from the sun, it's coming from all over the galaxy towards you. As I mentioned, higher mass and higher velocity, right up sometimes including a reasonable proportion of iron elements as well, which is a lot heavier. So these are the ones that are the most dangerous and the most difficult to protect against. So why don't we have to worry about them on Earth? It's because Earth's atmosphere and our magnetosphere, which we'll talk about both, protect us. Let's talk about the atmosphere first. So the upper layers of Earth's atmosphere, including the ozone layer and high up the thermosphere, the ionosphere, that quite happily absorbs the solar ultraviolet, the X-rays and the gamma rays. They get absorbed, the elements up there, just particles, just quietly absorb them and get ionized, for example, the ionization layer and so on. So they get absorbed. The galactic cosmic rays come in, they don't get absorbed, but what they do, they strike particles high in the atmosphere, mostly oxygen and nitrogen. They strike them, collide with them, and they fragment, which we'll talk about. They lose a lot of energy in the process and fragment up to smaller pieces, down to muons and pions and so on. And by the time you get down to Earth's level, there's very few galactic cosmic rays to speak of. You do get them, but they're very few to speak of. And they've lost a lot of energy through just colliding with particles high up in the atmosphere. So our Earth's atmosphere protects us a huge amount. Then our magnetosphere, because our Earth has a molten iron core that sloshes around and you've got convection going up of the heat rising and so on. And the combination of all that movement, of course, iron is electrically conducting and it's liquid form, it's sloshing around, it generates magnetic fields. And so you get these magnetic field lines going around the Earth like that, and that's called a magnetosphere. Magnetic field lines that form a sphere, magnetosphere. So we've got one of those, and that protects us. You might say, well, how does that protect us? This is obviously a not to scale diagram, but you can get the gist of it here. So here's the sun with the solar wind blazing out here with all the particles, and here's the Earth with its magnetosphere, and you can see it deflects the charged particles, because charged particles get affected by magnetic field lines. So the magnetic field lines deflect most of the solar wind away from us. So that's huge protection for us. Now, also because of that, some particles at this end over here, the tail end of the sun at the night time, sneak back in through here under the line, and they'll often then they'll follow the magnetic field line down to the poles, and that's where you get your aurora, is because of the coming down to the poles, and particularly that's where they sneak in at the nighttime side. And because of that, a lot of these charged particles get trapped in Earth's magnetosphere. They get trapped in here, they spiral to the pole, and then they'll go backwards and forwards to the pole. And they form what they call the Van Allen belts. It was a Dutch guy who first described them, or he first hypothesized that most likely there must be some belts up there with radiation at the time they sent up satellites, and yeah, you're right. So they've mapped out there's two Van Allen belts here, and the outer one here is a very rich in electrons, and that's mainly from the solar wind. And then you've got the inner belt. So these belts here, this is a slice. So you imagine this is a cross section, if you will. These are in a donut shape, like a toroid or a donut shape. So the inner one here is proton rich, And those protons come from galactic cosmic rays. And you might say, well, how did they get in there? And that's when these galactic cosmic rays strike the nitrogen and oxygen particles in the upper atmosphere. They then will fragment, and we're going to talk about secondary radiation shortly, but they fragment and get broken up, and often when they do that, you get neutrons formed. And the neutrons then will often go back up into the upper atmosphere, get deflected upwards, and then they decay into protons and electrons. So that's how the protons get there trapped. And these are fairly high energy, these protons as well, sitting in here. All of these, you might say, if the solar wind's not too bad, and a few of them get trapped, well, what's the big deal? Why are we worrying about it? Because you've got magnetic field lines in here, because they all gravitate towards the two poles of Earth, they get accelerated. So all these particles are at high velocities, electrons and protons. So that is something that you've got to keep in mind for the astronauts. Now, here is something to throw in with the mix, because you might say, well, how much do these belts extend from? And just very roughly, the belts extend, the inner aspect of the inner radiation belt, it's about 600 kilometres from the surface of the Earth. And it goes out to the outer aspects of the outer radiation belt is about 60,000 kilometres. So it goes out a reasonable distance. And it varies a little bit in intensity and its exact shape and its exact size. Someone asked me today, is it exactly 600 or 60,000? And I said, no, it varies. Look, that's just sort of a rough idea. It can vary according to the solar activity of the solar wind and these solar particle events. So it does vary a little bit. But that's just very roughly gives you an eye. Now, of note here, the International Space Station's average orbit is about 400 kilometres. So it's inside the belts and inside the magnetosphere, so it's protected to a degree, but it's above our atmosphere. And you saw how protective our atmosphere is, how good it is for us at keeping away radiation. Now, there's something else to add, and that's not the full story, is what we call the South Atlantic Anomaly, or the SAA. And that's, did you notice here, the magnetic axis is slightly askew from the rotational axis of Earth. And because of that, the belts down near this little area of the South Atlantic Ocean dip down to about 200 kilometres. So the ISS goes through that SAA probably about 8 or 9 times a day, but only for about 5 or 10 minutes. It's not a biggie. The ISS goes around the Earth every 90 minutes, which means it does about 16 orbits in 24 hours, and it's about 1 of every 2 orbits it goes through the South Atlantic Anomaly. So it's about 8 or 9 times a day, but it's only between 5 and 10 minutes that it goes through it. They don't have to take any special precautions. They just do 2 things: no spacewalks, and they'll power down any sensitive instruments they happen to have in the space station. Otherwise, life is normal. They don't put on any special things on or scurry away to any parts of the station. So it's not a biggie, but they are aware of it. And it contributes to a lot of their accumulation of the radiation exposure. So that's, where does radiation come from? Why is it a problem only in space? So let's have a look at what effects it has on the body. And there's 2 effects, main effects. You can split it into acute or chronic. So acute in medicine refers to something that's rapid onset and usually short duration, something that comes on really quickly and sharp and fast, hard and fast. And typically your solar particle events are the cause of this, and it causes what we call acute radiation syndrome, or ARS. And they are caused by the solar particle events that occur over a number of hours, sometimes extending up to days. An acute blast of radiation like that typically first affects the cellular organs in the body that have a high cellular turnover or reproduction rate. The gastrointestinal tract, you'd know, the first one that comes to mind. So patients will, there'll be patients by this stage. Nausea, vomiting. You might think, well, how does that settle in so quickly? And the research suggests that probably what happens is those gastrointestinal cells get damaged. They release serotonin and various other chemicals that go to the Niagara substantia nigra part of the brain that could involved in the nausea and vomiting system of the brain. So that's probably how they act. But you quickly get, within hours, nausea, vomiting, diarrhea, and that leads to a very dehydrated and weak astronaut. Bone marrow, that's usually the bones in your sternum, predominantly at various places, hips, bit of skull, but predominantly sternum and your pelvis, and that's where all your red cells are produced. So you've got plenty of red cells to carry oxygen around, your white cells to fight infection, and your platelets to help your blood clot. So they have a very rapid cell turnover. So they get affected. So you can get an astronaut who might be anemic, low in red cells, prone to infections and prone to bleeding. The central nervous system gets affected. That's very sensitive to radiation. So you can get confusion. Ataxia means unsteady on your feet, what most students are like on a Friday night. Convulsions, and then coma and death. That's quite critical. So yeah, essentially you can result in a very acutely unwell, ineffective astronaut who's quick, needing a medical attention. They do have things like intravenous fluids on the space station. They have basic stuff. They have anti-nausea, vomiting drugs. They have intravenous fluids that they can give if need be as well. But you'd rather prevent it all. The other one is chronic. So chronic means, as a rule of thumb, something that's slower onset, usually 6 weeks is sort of sometimes a bit of a rough guideline, but it's something that's slower onset and its duration is longer. So that's what the word chronic means. Often you use the word, oh, I had a chronic headache yesterday. And you think, it's the wrong use of the word. Yeah. So that's what chronic means, slow onset and long duration. And of course, carcinogenic mutations, that's your DNA. DNA, you get a damaged DNA, it can take generations, it can even take years to come out. An abnormality. It can take up to 30 reproductive processes of the cells before it comes out. It doesn't declare itself automatically. So that's usually chronic. Immunodeficiency with the immune system gets damaged. Coronary heart disease has been linked in with radiation. Infertility, you can't have a bunch of unwell, infertile astronauts going up there to colonize Mars. Oh, we're all infertile. Houston, we have a problem. Yeah, cataracts, so you have blind infertile astronauts. And cognitive, they'll be a bit confused, they won't know what they're doing as well. So all these things, you'll have an ineffective astronaut in poor health. So it's not a good look, guys, yeah. So that's the chronic effects. So so how much radiation is acceptable? You've got to take something, you've got to harden up somehow. So they use the Sievert as the unit, and it's the unit of, it's lifetime, you look up here for this, it's lifetime, it's accumulation, allows the accumulation of radiation, allows the lifetime health effects from ionizing radiation exposure. So it's a cumulative thing, and it takes in the effects on your health, and it accounts for, it's something that's calculated, the types of radiation that someone's been exposed to, the sensitivity of the body organs that have been exposed to the radiation, and from there they calculate, they've got algorithms on, they calculate the risk of cancer. To give you an idea of put things in perspective, we'll move on Earth, we are exposed to about 3 millisieverts of radiation per year just on Earth. How? As I mentioned, the galactic cosmic radiation, a little bit does come through, so you've got a little bit of that. Natural radiation coming up from the Earth, radioactive rocks and the like. Uranium, that's uranium and thorium and potassium are in the rocks in Earth, and they're quite radioactive. And in particular, uranium, it doesn't decay straight to lead. There's a whole decay chain. And one of those items in that chain is radon. Have you heard of radon gas? Yeah, radon's radioactive. And you inhale it, and there's a high incidence of radon exposure in people who live in basements or down underground or in basements or low levels and so on. And radon is the second only to smoking the cause of lung cancer. So, you hear stories of, Uncle Bob died of lung cancer. He didn't smoke a cigarette. There was no secondary smoking or anything like that. There was every chance Uncle Bob might have been living in a basement or something like that. So radon is the second largest cause of lung cancer, second only to smoking. So fun fact. I wouldn't call it fun, but fact. Chest X-ray, only 1/10 of a millisievert. You move up to a CT scan and you're up to 7 millisieverts. So it just gives you an idea of our day-to-day radiation exposure. So now here's something else to add to it, is to the lifetime cancer risk is both gender and age sensitive. This is relevant to the astronauts, really relevant to the astronauts. Why? Females, of course, breasts and ovaries are very sensitive. They're involved with reproduction and so on. They are very sensitive to radiation, so you've got to factor in that. And lung cancer, don't know why, but lung cancer is more prevalent in women than men, all things being equal in statistics. So no one knows why, but it's just a fact. So females are more vulnerable, more susceptible to radiation damage. And youth, because it's a lifetime cancer risk, you get a young astronaut, say 20, he or she, hopefully will live for another 60 or 70 odd years, so they've got more time to develop a cancer, as opposed to someone who, say, 70, they've maybe only got another, say, 10, 15, 20, 25 years. So they've got a shorter time, so less likely to develop a cancer. So that is relevant. Moving on, NASA's career limit, they've decided they've set it at a 3% increased lifetime risk of dying, so fatal, from radiation-induced cancer with a 95% certainty. So that's how they calculate. They take into effect the age of the astronaut, the gender of the astronaut, the radiation exposure, the type of radiation, the organs that have been exposed, and they calculate it, and they set the limit at a 3% increased lifetime risk of having a fatal radiation-induced cancer with a 95% certainty. So, of course, as I mentioned, that varies between astronauts. For example, Megan MacArthur, she was 29 when she got selected, so a 30-year-old female, at 180 millisieverts, she's at a 3% limit. Bang, career over. And you'll show shortly that, there you go there, let's just jump ahead. 1 year on the space station is 240 millisieverts. So about 9 months or so on the space station, career over. As opposed to a 60-year-old male, say Scott Kelly, now in his 60s, if he went up, again, he went up in his 50s, but just using an example, he could tolerate up to 70 millisieverts before he's considered the 3% risk of a lifetime risk of a fatal cancer from radiation. NASA, however, caps it at 600 millisieverts. They've decided no more than that. Out of interest, Canadian Space Agency and the Russian Space Agency, they're 1,000 millisieverts, just right across the board. Which is about 5.5% risk. So I think it reflects a lot of it as NASA, America's medico-legal sort of side of things, the litigious society, they're more aware of it. So, just moving on, before I come to that little bit down here, they had a radiation detector on the Curiosity lander when it travelled to Mars. And they took the recordings from there, then put it through a simulation and extrapolated the data. They worked out that a 3-year round trip to Mars, including a 500-day stay on Mars with current technology, which is about 8 to 9 months either way travel, an astronaut would be exposed to about 1,000 millisieverts, which is 5.5% increased risk of a fatal radiation-induced cancer. So that just keep that in the back of your mind. Think, oh, it's out. I'm going to show you as we go on. We'll overcome that. That's just today's technology. So the future is, and it's the women who are pushing this. They are pushing for a limit of 600 millisieverts, independent of age or sex. 600 millisieverts just across the board. The woman is saying, hey, look, you've informed us. We are fully informed. We are pioneers. We will take the risk. Thank you very much. Show us where to sign. Just give us the document. We'll sign it. Thank you very much. So a lot of the women coming forward and saying that. So that is quite a thing that they're debating at the moment, whether they can sign a waiver. That's interesting. So, okay, so that's how much radiation is acceptable. Let's move on now to countermeasures, and I'll show you how I'm going to change all that right around. So these are the 4 big ones, looking at your shield, what sort of shielding you're using, your timing of your launching, your duration of your travelling there, and also just affecting monitoring of astronauts in the sun. So let's have a look at shielding. So it comes down to spacecraft design, including a storm shelter, which we'll look at. The hull of the space station and also the Orion capsule, which we'll talk about, is made as aluminium. However, there's a big risk of secondary radiation, which we'll talk about. And I mentioned here the aluminium hull and spacesuits are easily protected against the solar wind. So that's not a problem. We're really targeting SPEs and galactic cosmic rays. So what is secondary radiation? Well, that refers to when these HZE, H stands for high energy, Z stands for high mass, and the E is for the high energy. So it's high mass, high energy. So you often see HZE. So these high energy particles, when they strike the spacecraft or an astronaut's body tissue, it rams into it, and either the charged particle itself, the ion, and or the tissue fragments into smaller particles. And from there, it creates a particle, as I've tried drawing there. I hope that all makes sense, but I've tried drawing that there. You'll see it creates a cascade. And it just keeps snowballing and striking more and more particles, striking other particles. That gives rise to more particles. And it creates this cascade of much more smaller but equally damaging secondary particles. That's the big problem. So secondary radiation also includes X-rays and gamma rays. You might say, well, how do gamma rays form? Well, your galactic cosmic rays, they can strike particles, and sometimes you in decay, and you often get pions, and pions can be neutral or charged, and it's the neutral pions that they would decay into gamma rays, and that can happen in your body. Thank you very much. You can get pions. So all that is relevant, but it also produces protons and neutrons, and I underline and put an asterisk there. They can radiate up to 1 centimetre into your tissue, just from one of these galactic cosmic rays, one ray hitting your tissue, a cascade of secondary particles that can send energy. 1 centimetre of your tissue. That's a large amount of tissue getting affected. So, and of course outwards. So you're talking 2 centimetres either way. I've highlighted neutrons here. Neutrons, you might say, oh, they're neutral, they're fine, they won't cause anything. I'm going to show you, neutrons are far more dangerous than your protons travelling into you. Why? Because protons are positively charged and your particles in your body are charged, and they eventually get stopped. Your neutrons are neutral and they just keep going. They bury deep into tissue. They then strike particles, and then they then separate into your protons and electrons to cause a further cascade. So you've already had one cascade, you get neutrons going in, they'll travel in even deeper and cause a secondary particle cascade, if you will, and cause even more damage. So they're really important. And the other thing to mention is it comes down to how thick you might. Well, just have more aluminium, guys. Why don't we just crank up that hull? And here's the thing is, the thicker you get, you cut down your radiation as you get thicker and thicker until you get to about 30 grams per square centimetre of aluminium, which is about 10 or 11 centimetres thick, yay thick. And after that, it becomes counterproductive. Your secondary radiation starts going up because you're becoming a hindrance. It's a thing that's going on there. So there's a sweet spot. And I'm going to show you shortly how maximum 30 grams per centimetre, which is about 10 centimetres thick. The ISS and the Orion only have a hull of about 5 millimetres, half a centimetre. And you might say, why? There's some sense here. One is you've got to put the thing into orbit in metal ways. Even aluminium is relatively lightweight, but it is weigh. But the other thing is it takes up space. You can't have a craft 10 centimetres, yay thick. You're going to cut down your room inside the craft. But the other thing is your secondary exposure and stuff, but that is actually sufficient. Your prime purpose of the hull is to protect a bit of radiation, yes, but also is to maintain a pressure chamber, if you will, for the astronauts to remain pressurised. You only need 5 millimetres of aluminium. And the hull of the Orion capsule and the ISS has other layers. It has a bumper panels of aluminium, so in front, which are literally bumper bars, if you will, or bumper panels, and they are just to block micrometeorites and so on, just debris physically striking the craft, and they protect that. They can get damaged, that's fine, not a big issue. You can replace bumpers. So they have a bumper layer, and that also affects radiation, but they have a layer, this is called a Whipple layer, and in between the bumper layer and the inner hull, they'll have Kevlar. And Kevlar is really, really strong. It's it's not quite a polymer. It's a man-made material, but it's really, really strong, and it's effective against debris, micro debris, and micrometeorites, and so on. But that significantly cuts down radiation in its own right. It's effective as polyethylene, which we'll talk about. So Kevlar is very, very good as well. So you get those three layers are designed that way, A, to protect against meteorite collisions, give you a reasonable amount of radiation protection, and create still lightweight enough and minimize secondary radiation. So that's the sweet spot, so to speak, of your layers. And that will reduce radiation fairly significantly by about 60% or so of that. Now, the other thing I mentioned here, usually when you often give this talk on sort of general audiences and on ships and the likes and stuff, you'll always get one or two people come up to you afterwards, why don't they just make it lead? Why don't they make the spacecraft lead? And I go, well, you've got three problems there. One is lead's really heavy and you've got to put that thing into space. And lead is not strong structurally. It is not a strong metal. So, and the other thing with lead is effective against X-rays, hence the radiographer putting a lead apron on and scurrying away into the side room or lead-lined side room while you're standing there in front of the X-ray machine, which is all you're all feeling happy about. But lead is great for X-rays, but it does absolutely zero for gamma rays. It does zero effect for galactic cosmic radiation. Any particles, subatomic particles traveling any speed, lead does nothing. In fact, lead is one of the worst things you can have for secondary radiation. It's really conducive to secondary radiation. So you want to keep lead well away from your spacecraft. So that's the hull. Now, how about here? So what's the connection here? Water supply, polyethylene, I mentioned the Kevlar materials, particularly the water supply, H2O, full of hydrogen. Polyethylene is a polymer full of carbon, in particular, rammed-packed, rich in hydrogen. And hydrogen is so good as the number one material for protection against radiation. Why? Two main reasons. One is it's one molecule, one subatomic particle that's positively charged. So it's got the largest charge to mass ratio of any particle / subparticle thing that you can possibly have. One tiny particle that is positively charged. So it's really good at either blocking the radiation or these are particles from these galactic cosmic rays, blocking them or at least significantly slowing them down because it's high charge to mass ratio. The second thing is, which I've already mentioned, it's small, it's tiny, it's the smallest subatomic particle that we're talking about now. You can get smaller particles than that, sure, but the small realistic one, you can't break it down any further. It does not give rise to secondary radiation. You got nothing further, you can't split it into anything further, you can't split it into your quarks and so on. It's the smallest practical subatomic particle, is your proton. So hydrogen is the key to radiation protection, to shielding. And water, rich in it, and they'll strategically, even on the space station, they strategically have the water spread out around the spacecraft, around the station. And it's the same with our Orion capsule. They have their water supply strategically placed near around some of the wall-in cabin areas and so on. So in these, that's what this diagram is about too. It's an artist's impression of some spacecraft traveling to Mars. You can see they've got their water supply all dotted around the outside, protecting. So it's one of your best things. And the same with your polyethylene. So let's just talk a little bit about polyethylene. So the space station uses polyethylene for some of its lining. I'm just going to bring up the next little bit here. How effective is it? About 5 grams per centimetre, or about 5 centimetres thick, gives rise to about a 30% dose equivalence reduction. Dose equivalence means the potential biological harm, essentially, not to absolute radiation exposure, but to the final biological outcome or harm to your body. So a 30% reduction. You bump it up, double it, and you get it increased to 50%. So what they do, they've opted in the space station for the 5 centimetre. Why? You've already got a 30%. Remember, you've got your hull as well, and your Kevlar in the hull, and your water supply. Another 30% is great. To have to double the size of your protection to get a modest increase is not worth it. Why? The space station already, they're cramped for room in there. And suddenly you start lining the walls with something that's 10 centimetres thick, you're going to significantly reduce the size of your space within the space station. So they've opted for a compromise, a trade-off, if you will, for the 5 centimetres. And the second thing is that the space station is not just bits of jib-like walls where you just slap it up like tiles. You know, there's cables, there's pipes, there's instruments attached to the walls. So they just do it in little patches and they'll surround it. And they do it in particular around sensitive instruments on the space station. But the living quarters, in particular the eating and the sleeping quarters, are well lined with the polyethylene. Because if there's a solar storm, they can just stay in those areas. They perhaps shut down some sensitive instruments, and they can just go to those sort of storm shelter, if you will, of the space station, where they're going to get some extra protection. Now, put these up. These are your Artemis II astronauts. Reed Wiseman, the commander, pilot, Victor Grover. I always remember you, Victor, his name here, Victor Grover. I always pause on his name, I just think of Victor. Victor Grover, Christina Cook, and the Canadian guy, Jeremy Hansen. So those are the 4 astronauts that are going up. I thought, let's talk about them for a minute. What are they going to do in the space, with a solar particle event? And here they are sitting in their seats, or in their positions here. And look what we've got here. Down below here is their little compartments, storage compartments, where they store a lot of the equipment, water supplies, and just gear, clothing, and stuff. And that's it there, with them out of the seats, and you can see these little compartments in here, and that's their storm shelter. I put this diagram in here because it gives you a better idea of them here, positioning it to be travelling through space. Not that there is an up or down in space, but the storage areas are at the back here. And look what's behind them. You've got the heat shield in here, and you've got the service module in here. So that's the thickest part of the spacecraft. And they found when they went Artemis I, data came back, they had sensors all over the spacecraft that had significantly, just behind the heat shield, had the least amount of radiation exposure. So what they do is they climb into, let's just go back. So they climb in, they open these compartments up. There's 4 compartments. They're relatively tiny. Each one has just got enough room for an astronaut to go in and crunch right up like that. They take all the gear out, and they make like a little hut. Remember as kids, you'd make little huts and things like that. They just stack up all equipment that was in there, stack it around them for extra protection, and they huddle their backs to each other, and they huddle, and they can sit there for a few hours at a time until the solar storm passes, or the intensity passes anyway. So that's their protocol if they get a major solar event while they're going in the Orion capsule. So it's there. So how about for the Van Allen belts, how they go through there? And geez, you get these people, these flat earthers and stuff, who say, they didn't go to the moon. Why? They couldn't have gone through the Van Allen belts. Okay, is that your argument? Let's just get clear on this. Yeah. So that's your argument. I didn't go to the moon. Van Allen belts. Right. What do you know about the Van Allen belts? They know nothing about the Van Allen belts. So yeah. Van Allen belts aren't an obstacle. They're something you've got to plan around. So a lot of it's the trajectory, the Earth, what they call Earth Park orbit. That's where they just do a few orbits of the Earth. They don't just charge straight off to the moon. You want to assess your capsule, make sure that everything's functioning purpose before you commit yourself to travel to the moon. They sit in an Earth Park orbit for a while, just checking all their systems out. So that's underneath the belts. And then when they go through the belts, they take the shortest route, low inclination, just get through those belts at top speeds. They take that inner proton belt. Takes about between 30 and 60 minutes to get through there. They're travelling, 38,000 kilometres per hour at this stage, fairly quickly. The outer belt takes about 60 minutes to get through. And the spacecraft orientation, as I mentioned, they had all these things, and what they did do is they changed the orientation of the Orion capsule as Artemis I, as we were going through the belts, just as a bit of an experiment with all the sensors, the radiation sensors working, and they found that you have 50% reduction in radiation exposure to the astronauts just by turning your spacecraft around, so your thickest bit, your heat shield and your service module, is facing as you're heading towards the protons and electrons and so on, your charged particles. So it's the orientation of the spacecraft, point your thickest structure towards the direction, 50% drop in levels just from doing that. The Artemis I data, they had, which I'll show you shortly, they had 2 mannequins up there as well with sensors all over them, but they had sensors all around the craft. Of that 28-day mission, the entire 28 days, total exposure time in the capsule was 30 millisieverts, only 30 millisieverts, say 10 years just on Earth, for example. And the total exposure on the Van Allen belts, going through the belts on the way out to the moon and coming back again, combined, only 3 millisieverts. That's just what we have in a year. So it is not a barrier. So it's a consideration, and you minimise your orientation of your spacecraft and so on, and go through the belts with a good trajectory. But there you go. That's next time some person bails you up and says they didn't go to the moon because of the Van Allen belts. You tell them they also probably believe that birds are just governmental drones watching us all. Birds aren't real. That's the sort of stupidity that dribbles out of their mouth sometimes. Don't get me started. Okay, let's carry on. Now, here's another, this is really cool. So this is an Israeli company produced the Astronaut Radiation, and it's a proprietary, so they've made it a commercial secret, if you will. And they've made this material for a vest that's really rich in hydrogen, and it's intended for astronauts to put on just at the time of these solar particle events. They can just put it on. It's designed to protect the 6 main radiation sensitive organs of the body: breasts, lungs, stomach, colon, ovaries, and bone marrow. Those sort of purposely designed to protect those 6 sensitive organs. Successfully trialled on Artemis I, which I'll come to shortly, but also the International Space Station astronauts wear it, who have been experimenting with it, for the prime purpose of seeing if it was comfortable, whether they could put it on quickly, and whether it was comfortable enough to work it for a few hours or maybe even a full day with it while wearing it. And it came back flying colours. The astronaut said, no problem, put it on easy, didn't slow us down, no issue at all. Remember, it's weightless up there, it's not like a heavy dragging you down. So they said, no problems, we could keep working, living quite happily for a day or two, quite happily with it on. So here's the 2 mannequins on Artemis I, and one you'll see over the far one over here, that's got the vest on, this one hasn't, and a 60% less overall radiation exposure to the entire body, but to the vital regions, 90% less exposure, 90% just by putting this vest on. So you can see where I'm leading with the argument. You know, that whole thing, all the stuff can be overcome as technology develops. So here's something interesting. This is a new material. It got developed first about 15 years ago. It's really expensive to make, but they're starting to get better at commercially making it. And you get boron and hydrogen, well, you get boron and nitrogen, boron nitride. And you bring them together and they form hexagonal shapes, and you can make little tubes from there. And out of all the gaps in these hexagonal shapes, you impregnate it very readily with hydrogen. So you can make this really strong new material rich in hydrogen. Hydrogen, as we've discussed, how that's by far the best element and all, best atom for your radiation protection. But the secret is too, boron 10, your basic one, 5 neutrons and 5 protons, so boron 10 has an affinity. It's got an isotope called boron 11, and it loves to bring it on, give me another electron, come on. So an electron and a proton, and sorry, start again, a neutron in particular, the isotope of an element, same number of protons, but an extra neutron. So it says, bring it on, give me another neutron, I want to become boron 11. And it has a very high affinity for neutrons. So suddenly you've got this material that's rich in hydrogen and rich in nitrogen. So it's fantastic. And remember what I told you about neutrons? They are really dangerous stuff. You don't want to make too many of those in space traveling at high speed. So that's really great. Now here's the other thing about its physical properties. So it's brilliant radiation shielding, very flexible, very strong. It is 100 times stronger than most forms of steel and 50 times stronger than carbon fiber. Really, really strong, and it's electrically insulating as well. So it's really flexible. So it's ideal for habitats, rovers, spacesuits, spacecraft. It's going to be one of the materials of the future. But once again, you can see where I'm heading with this. Today's technology, no. Tomorrow, yes. So that's shielding. Time and length of launching. As I mentioned, the sun goes through these cycles of maximum and minimum and so on. And the solar wind steps up, and you get these solar particle events as well, and you think, oh, it's all bad. It's not all bad news. There's another side to it. You got these galactic cosmic radiation, these high energy, high speed, high mass particles coming towards us. The solar wind offers a little bit of deflection against that. So if the solar wind and these particle events that are pushing outwards, that significantly deflects and minimizes the amount of galactic cosmic radiation that we within the solar system get exposed to. And remember what I told you, it's the galactic cosmic rays trump everything else. They are your most dangerous and difficult to shield against. So they worked out if you time it about 6 months after solar maximum, you can reduce your radiation exposure going to Mars by about 50%. Consider that, another 50. Remember, the hull is about 60%, polyethylene's about 30%, your vest is 90%, you're another 50. You start adding these up, yeah, we're getting to Mars. And that was actually something I didn't mention there too, is remember in particular that 500-day trip, 500-day stay on Mars, that over a 3-year trip to Mars, was 1,000 millisieverts. Just by timing, you've dropped it to half, 500 automatically, and that's under your magic 600, which the astronauts are all gunning for as a limit. So how about propulsion systems? Currently, we use chemical propulsion, liquid fuel, and that's great in terms of rapid acceleration and deceleration and so on, but it weighs a lot. It's just heavy to lift up. You can see a rocket launching off the pad, particularly the old liquid hydrogen oxygen, the Apollo and stuff. 85% of the mass of a rocket is the fuel to get it into orbit. Consider that. So it's not very cost effective, but it is good. It's got its advantages. In the future, NASA's already about 2 or 3 years away from having these now experimenting with nuclear power. And that's where you get uranium, radioactive uranium that heats up stored liquid hydrogen, excuse me, and converts it into hydrogen gas, and you expel that out the back of your spacecraft, and that's your expulsion. That will halve the transit time to Mars. Ion propulsion, they're already using that already. That's used in a number of unmanned craft. And that's where you get something like xenon gas. You bombard it with high energy electrons, which bumps electrons off it and creates xenon ions, and then you put electric field over here, and the charged xenon races out, and that's your propellant as well. That uses a lot of electricity, but it's very fuel efficient, and it starts off at slow acceleration, but you can get up to high speeds with that as well. So they've got their pluses and minuses. Probably it'll be a hybrid. Use your chemical combustion for your acceleration and so on, and then rely on your nuclear and your ion propulsion. As I mentioned, these technologies are well advanced. Okay, then there's effective monitoring. And it comes in passive and active monitoring of the astronauts' radiation exposure, but also monitoring the sun and its activities as well. So the astronauts have personal dosimeters. They all wear these 24/7. And it records the type of radiation, the type of particles, the energy levels. It records all those things to calculate millisieverts. They have them, and when they go back down to Earth, they get them read, interpreted, and told, hey, break the news to the astronaut, this is how many millisieverts you've been exposed to on your time in the space station. They also have them dotted around in strategic places in the station as well. Then you get active. So those are sort of more passive, that in retrospect, but active ones, real time. They've also got newer particle detectors up there, which will tell you exactly what's going on in the station right now, that they can read right then and there. And then, of course, which is a whole science in itself, the developing, learning and understanding how the sun works better and better. So get more predictions of when a solar storm is happening, when it's going to happen perhaps, and or if it is happening, get an early warning and so on. So they're trying to understand that so they can predict, or at least get an idea of what's happening and inform the astronauts a lot sooner. Hey, it looks like a solar storm is brewing, put your vest on, get into your storm shelter region and shut down the sensitive instruments on the station. Thanks very much. And of course, no spacewalks. Two other things I want to mention here. Monitoring bioeffects and biological protection in the future. So already they're doing it astronauts. You'll see plenty of pictures of astronauts taking blood and blood samples to do a lot of research up there. Lymphocytes are a type of white blood cell. In particular, their chromosomes are very dynamic and change. And looking at the chromosomes of these lymphocytes tell you two things. One is they'll tell you reflect how much tissue damage has happened to an astronaut. And two, here's a really interesting thing. They can predict the sensitivity of an individual to radiation exposure. So think about that. So they'll tell you, the astronaut, you seem to be, you've copped 240 millisieverts on that last year in the space station, but you actually haven't done that much tissue damage to yourself, looking at your lymphocyte chromosomes and that. So, but also that person's obviously less susceptible. But here's something really interesting. You could even say is a little bit, the ethics of it all too. It allows screening for astronauts in your crew selection. Who are you going to send on a long journey? You got, say, 20 astronauts lining up for a 10 astronaut job, and you identify 10 of them who are really radio resistant. They've just got good genes. They're less likely, less vulnerable to radiation exposure and tissue damage. Who are you going to pick? So, yeah, that's where it's all perhaps heading too. And then this is interesting. All just nutritional technology, pharmaceutical technology, that they're trying to increase the resistance of astronauts to radiation such that minimal tissue damage. And dietary nutrition, and you might say, well, this is pretty obvious, good whole food supplements with minerals and vitamins, antioxidants, and so on. Isn't that pretty basic? It is for us on Earth, but a lot of things day to day we take for granted. You try and get fresh produce and whole fresh foods and stuff on the space station. What do we do with it? We refrigerate it, we freeze it, don't we? That, refrigeration, room and energy is precious on spacecraft. You don't have fridges and freezers everywhere, left, right and centre. So it is a whole new technology. A lot of the astronauts, they have their food and stuff in plastic bags, they've got to rehydrate. That is a whole science that's opening up, is making astronauts' food as more nutrition and of course supplements, your vitamin E, and the astronauts do take supplements. Vitamin C and E are very good antioxidants, for example. Vitamin D for their bones, because they're not exposed to the sun and so on as well. And then pharmacological, this is very exciting, that they're coming up with these medications that if you know an expected solar particle event's coming up, you can take something beforehand that's going to give you protection, or admit straight after an event to accelerate. I mentioned that cells can recover and repair damage to a degree. That'll accelerate that recovery process within cells, and also other medications that are developing that can activate the body's natural defense and repair mechanisms. This is also having spin-offs in oncology departments. Cancer patients who are getting radiotherapy and the stuff, you want to hit the cancer hard. So you want to develop drugs that'll help that, but also you want to protect the healthy tissue. So you try and get that right balance with patients, or patients who've had radiotherapy, they've got bad side effects from healthy tissue damage, and you can help them with this as well. So this benefits oncology departments and patients and society as well. So we're just wrapping up now. Here we go. Oh, fine. Yep, so summary and conclusion. Let's wrap up. So ionising radiation, you know what it is now, that is a significant risk. You know what it is and you know what it does to the body. Prime radiation source, you now know it's the sun. Solar wind's not a biggie, but certainly these solar particle events are. And the galaxies, these high energy events such as supernovas and gamma ray bursts, spitting out a higher proportion of high mass, high energy, close to the speed of light particles, they're the biggie. So what can it do to astronauts? Acute illnesses, vomiting, diarrhea, dehydration, confusion and so on, and affecting their bone marrow. Chronic illnesses with cancers and just diseases, heart disease, cataracts, infertility. Countermeasures, you saw that, a better shielding of the technology. Hydrogen is your key, your polyethylene, your optimal for your aluminium hull. You've got these the Astrorad vest, often 90% production. We've mentioned your hydrogenated boron nitride nanotubes. We've mentioned timing, to time it in just 6 to 12 months after your solar maximum. Propulsion, newer propulsions, technology has been developed, and better monitoring of the astronauts and the sun. And of course, the future with nutrition and pharmaceuticals is very beneficial. So my really conclusion is the radiation will not be a showstopper for going to Mars by 2040. Just putting this on here. So,
Battery 100%.
here we go. So next time you see astronauts having fun like this in space, or doing whatever in space, being weightless, and you say, oh, I can see that, the prolonged weightlessness, we're also told that's bad on your muscles and bones and every organ of the body. But just stop for a minute and think about the hidden danger of radiation and how critical it is, but you can't see it. You can only see the weightlessness from up in here. So it's not all fun and games. But I also just want to show you there is some fun and games in space. Even gorillas have got to be careful of radiation in space. And that, my friends, is astronaut radiation exposure. Thank you. Okay.